All right. I am really excited about today's topic. And let me just give you a little background why. When my son was young, he was passionate about model rocketry. And 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 now he's an aerospace engineer working for the Air Force. But when he was young, model rockets were his thing. And so when he was in high school, we actually put together a class. He and I taught this class called An Introduction to Rocket Science, where we taught a little physics, a little aerodynamics, and then we built rockets both from kits, and then the students designed their own rockets. And so we sort of co-taught this. But then when he went off to college and had summer internships and stuff like that, my expertise is not in rockets, but I do love physics and math. So I kind of morphed the class into a class that I called the Physics of Motion and the Foundations of Calculus. And so I've taught that. It's at a middle school level, for several years now. And so I've got like hours and hours of material on this subject, mostly at a middle school level. So I kind of get excited about making that connection between physics and calculus. Because physics, or calculus, was invented to solve physics problems. It was invented by Isaac Newton when he was a young 24-year-old college student. And he was sent home because of a pandemic in London. Well, maybe not a pandemic, but at least there was a plague in London. And so I guess he had some time on his hands when he invented calculus. So, and I think that motion is something that we experience daily, and so it kind of makes intuitive sense to us. And so when you teach calculus in the context of motion, it just seems more intuitive. So this is our one chapter where we get a chance to make that connection between calculus and physics. And so that's what I'm going to try to do today, and try not to get too carried away with too many examples. I had to really restrain myself to pare it down to just just the important examples. So anyway, so let's get started with that. And first of all, I want to define I want to introduce some vocabulary, because in physics, there's some vocabulary that's used fairly precisely. One of those terms is displacement, and displacement is a distance measurement, but it's the distance relative to some reference point. And it's called a vector quantity because it has a magnitude and a direction associated with it. Okay, so I think your book uses mostly distance, but in order to use only distance, they have to limit their discussion to only positive velocities. And so I'm going to use displacement, because I like displacement. Displacement is actually easier in the long run and more useful. So I'm going to use the term displacement in this lecture, but displacement is a distance measurement. And if any of you have ever taken any sort of physics in high school, you probably learned that in physics there's a distinction between speed and velocity. So speed is just what we call a scalar quantity. It just has a magnitude and no direction. So you could be going 60 miles an hour north, or 60 miles an hour south or east or west, or any direction. Velocity, though, is in physics is considered to be a vector quantity, so it has a magnitude and a direction. And the same with acceleration. It's a vector quantity. So velocity is how something's displacement is changing over time relative to a reference point. And acceleration is the change in something's velocity over time. Right? So if you're speeding up or slowing down, right, your velocity is increasing or your velocity is decreasing, then you have acceleration. And in physics, we use it as a vector quantity. So what I want you to notice in these definitions is that basically, velocity is a rate of change. It's the rate of change of displacement over time. And so that means that if we have a function for the displacement of some object, then the first derivative of that function is the velocity. And acceleration is the rate of change of velocity. and velocity is the rate of changes of displacement. So essentially the acceleration is a second derivative of displacement. Okay, so we're working with, you can see the connection here with calculus, that the velocity is the first derivative and acceleration is the second derivative of displacement. So and we've been working up to this point. We've been working on derivatives, taking derivatives of a function, finding the rate of change of a function over time. But oftentimes we're given information about acceleration or velocity. We're given information about the first or second derivative, and we want to figure out something about the original function. We want to know if we're given some information about velocity, and we want to know something about the displacement. Or we're given information about acceleration, and we want to know something about velocity or displacement. So it would be nice to have some way of going backwards, to go the other direction and work from a derivative and find information about the original function. And that's really what this whole chapter is about. Chapter 11 is all about, we're getting into integration, okay? And so today we're just going to confine our discussion to the applying these concepts to linear motion. Okay, so we're going to look at linear motion, which means motion in one dimension. Now, motion in the real world is three-dimensional, but really we can just take a three-dimensional problem, break it up into one-dimensional problems. So one-dimensional motion is very important, even though it seems pretty simplistic. We're going to focus on one-dimensional motion. All right, now, in one-dimensional, whenever we're dealing with motion and we're dealing with vector quantities, we have to establish a frame of reference. And when we're limiting our discussion to one-dimensional linear motion, that's easy because we can just use a number line to establish a frame of reference. On a number line, we have an origin, right? We have the origin, and then everything is, on either side of the origin is measured with respect to the origin. So if we're here at 6 on this number line, we're 6 units away from the origin, right? It's telling us we're 6 units away from the origin. Okay, and then we also have a direction, right? So positive 6 means we're to the right of the origin if we have our number line set up this way. And if we're down here at negative 6, then we're to the left of the origin. Okay, so the direction is the number line makes vector quantities easy because we can just use the positive or negative sign to indicate direction. Okay, so if we take a look at this number line here, we have an example here with two objects. These seem like pretty straightforward questions, but I just want to just get you used to this concept of displacement. So here, object A, or here, this object has this point right here, and its displacement from the origin is it's 4 units, right? It's 4 units to the left. And so we would say that it's negative 4 units, right? That's its displacement with respect to the origin, okay? Now, point B over here is at 6. So it's at a positive 6. I don't have to write, I could write a plus sign if I wanted to, but I don't have to write a plus sign. It's 6 units to the right of the origin, so it's at positive 6 units. All right, now let's look at the velocities. We're given some velocity information. Now, point A, even though it's to the left of the origin, it's moving toward the right. It's moving toward the positive direction. So we would say that this has a positive 3 units per second. So I don't know, I don't have a scale on this as far as is it centimeters, or it's not like a standard unit of measure. So we're just going to call it units, units per second. Okay, so this velocity is 3 units per second in the positive direction, right? So it's moving in the positive direction. So positive velocity just means that the displacement from the origin is increasing. Okay, so Now, but that can mean two different things. You can see in this, but we're getting closer to the origin, but it's becoming less negative. So that's why we say that the velocity is increasing, because the displacement is becoming less negative. But you could also have a point, say over here, moving in that same direction, and now it has positive velocity because the displacement is becoming more positive. So, but either way, it's moving in the positive direction. All right, so this other example, we'll take point B. Point B is moving at a speed of 2 units per second, but it's moving in the negative direction. So we say that it has a velocity of -2 units per second. And so negative velocity just indicates that the displacement from the origin is decreasing over time. And in this case, it's just becoming less positive, right? It's moving toward the origin. But you can also get a case where if you, say, had a point over here and it's moving in that direction, it's moving in that direction. Now, in this case, it's becoming more negative. Now, the displacement is decreasing because it's becoming more negative, but it is getting farther away from the origin. So either way, though, it's moving in the negative direction, right? The direction is indicated by the number line. So the negative direction would be toward the left, and the positive direction would be toward the right. Okay. All right. That's just the basics. Let's go on to example 2. Now, this is going to seem really basic to you. You're going to be like, why is she asking me this question? Sounds like a 3rd grade question here. All right, so you drive at a constant rate of 60 miles per hour for 2 hours. How far have you traveled over that time? So this is kind of one of those questions that, kids ask in the backseat of the cart. When are we going to be there? When are we going to be there? And you learn to look for the green road signs that tell you how far away something is. And, if you're traveling, you can assume 60 miles per hour down the interstate, and then it's just a mile a minute, and you can estimate how long it will take you to get to your destination. So essentially, you know what to do on this one, right? We're going to take the distance is equal to the velocity times the time, right? So in this case, if we're traveling at 60, and I like to write it oftentimes this way, miles per hour times 2 hours, right? The hours cancel, and then get 120 miles. Okay, so, but I want to look at this a little closer here. Let's look at the graph of distance over time, okay? Now, you can guess what this looks like, right? We're moving at a constant rate, right? The distance is changing at a constant rate, so we have a line, right? It's like the graph of this function is a line, right? I'm just going to draw a line here. All right, there's a line. Now, what's the equation for this line? Well, here, let's see, this is distance over time. I'm going to label my axes, right? Here's the equation of our line, right? It's distance equals velocity times time. The slope of this line is the velocity. So our equation would be d equals, in this case, the velocity is 60, so d equals 60t. And, we're assuming that we're starting at 0 distance, right? So our y-intercept is 0. And, if you're traveling 60 miles per hour, then after 1 hour, you've gone 60 miles, right? And after 2 hours, let's try this here, here's 2 hours, you've gone, oops, a little bit high, okay. You've gone 120 miles. All right, so that's what the graph of this looks like. Now, this is going to seem a little strange, I'm sure, but I'm also going to draw the velocity graph. Now, the velocity graph is pretty boring, right? It's just a constant 60 miles an hour. So if this is 60 on our y-axis, here's what it looks like, right? Here's time t equals 1, and here's time t equals 2, okay? That's a pretty boring graph, right? It's just a constant velocity, okay? But one thing to notice, though, is that when look at this area. Look at the area under this curve. Notice that the displacement, right? I keep saying distance, but this displacement, the area, right? The area under this curve is into a 60 by 20 rectangle, right? So it, and that is the same as our distance, right? So we have a 60 by 2, I think I said 60 by 20, 60 by 2 rectangle, which is 120, right? 60 times 2. So the area of this rectangle is the same as the displacement. Okay? So, so the thing to notice is that the displacement can be represented as the area under the velocity graph. Okay? So, you know, we just take length times width, and we get the area, and the area is the same as the displacement. Okay? So, let's go to another example here. Okay, this is just kind of this similar, only we've got, in this case, we've got velocity that's changing periodically. Okay, so in this example, you're going for this long bike ride on a apparently a long straight path. Okay, so it's like a number line. Now you go for 2 hours. You go at 5 miles per hour. So let's graph that here. So you're 5 miles an hour, constant 5 miles an hour for 2 hours. And then for whatever reason you slow down, and for 4 hours you are going 4 miles per hour. Okay, so there's your velocity at that point in time. And then for the last 3 hours you are traveling at 7 miles per hour. Okay, so we come up here, 7 miles per hour. That's sort of what our graph looks like. And we're asked to, well, so sketch the graph of velocity versus time. There, it's done, right? and we're asked to figure out how many miles you rode. Okay, so this is sort of like the other one. We can just take 2 hours times 5 miles per hour, right? So during that time period, you have gone 10 miles, right? So, but notice again, we can just look at the area under this curve, right? So the area here is essentially 10 feet, right? So, and during this next segment of time here, you've gone 4 miles per hour for 4 hours, right? So the area here is equal to 16 feet. And then finally here we've gone 7 miles per hour for 3 hours. So the area here is 7 times 3, which is 21 feet. Okay. And then to get the total displacement, right? The total displacement we're just going to add up those areas, right? So we can add up, oops, I meant to make an equal sign. Equal sign. Okay, so we're just going to add 10 plus 16 plus 21. So we get a total of 47 miles. Okay, so again, this is just to emphasize that the displacement, let's write it down here, displacement is the area under the velocity graph. Velocity graph. Okay? So that's the important thing that I want you to learn here, is that we can that the displacement is the area under the velocity graph, which is also saying that if the velocity graph is the derivative of the function, if we graph the derivative of the function, we can get information about the original function by looking at the area under that curve, that graph. So, okay, let's look at a couple more examples here. All right, so here we have a graph of velocity over time. And the first question is pretty straightforward. It's just we want to read the graph. How fast was this vehicle going 2 hours into the trip? So at 2 hours, right, we can just read off how fast we were going by looking at that point. Right, so the graph is telling us that at that particular moment in time, we were going 20 miles per hour. Now, the second question is asking, how far did the vehicle go during the whole trip? Okay, so again, we can figure out how far this vehicle went. We can look at the total displacement by looking at the area under this curve. Okay, and notice that each one, it's got this nice little grid, right? And each one of these squares is 1 unit in time by 10 units in velocity, right? So each one of these squares represents a distance of 10 miles, right? So really all we have to do to get the velocity, the total distance covered over this whole trip is just count up how many squares we have. All right, so I'm just going to make a note here that each square represents 10 miles. Okay. So if we count up all these, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. We have 13 squares, and each one represents 10 miles. So 13 times 10 is 130 miles. Okay. Now I could also do the same thing. I could say, oh, we went 10 miles an hour for 1 hour. That's 10 miles. We went 20 miles an hour for 4 hours. You know, so that's, or no, because it's 3 hours because we're starting from 1 to 4, right? So that's 60 miles, and okay, here we got 50 miles during this 4th hour, and then finally we went 10 miles in this last time segment. I could also do it that way, but yeah, just recognizing that each one of these squares is 10, we can just count them up and multiply. All right, so this next example sort of illustrates the distinction between displacement and distance. So we have an object that's, whose velocity is described by this graph, and we want to know how far away from the starting point did this object end up, and what was the total distance that the object traveled. Now, the problem is we don't have any scale on the time or the velocity axis. But we have to assume this is just both a linear scale of time and a linear scale of velocity. All right, so each one of these segments represents, an equal amount of change in velocity or change in time. And so if you notice, we essentially have a distance, in the positive direction of 3 units, right? So our displacement during these first 3 intervals of time is 3 units. Now what's happening down here? Down here, suddenly our velocity is negative, which means we're traveling in the opposite direction. So we're traveling back to where we started from. So here we have essentially a negative area, okay, because our velocity is negative. So we have a negative 3 units. So because our velocity is we're traveling in the negative direction now. Right? We turned around and we're going back to where we started from. That's what the negative velocity means. And so if we're traveling back to where we started from, then we're decreasing our displacement. Right? We're traveling back to where we started from. So the things to note is that this, like I said before, when we talked about the definitions, the negative velocity indicates that the displacement from the starting point is decreasing. Okay, so let me write that down. Negative velocity indicates that the displacement from the starting point is decreasing. Okay. So what that's telling us is that because we went 3 units in the positive direction, then we went 3 units in the negative direction, this object, the object in question here, whoops. Okay. So this object that's being described, whose velocity is being described by this graph, ends up back where it started. Back where it started. Okay? So its displacement is 0. Displacement equals 0. Now the other question that's asked is, what's the total distance of the object traveled? So if I went out and back from my house, I covered some distance. You know, if I went for a walk, which I should do, got to get some exercise today. You know, I covered some distance here, but my displacement is 0. So even though my displacement is 0, I still covered distance. So this object traveled a total of 6 units, right? So the object traveled a total of 6 units, whatever the units are for distance here. So even though the displacement is 0, right? So the displacement is your distance from your starting point, but the distance is 6 units. So this example just illustrates the difference between displacement and distance. Okay. So, all right. Now we're getting into the meat of it here. Let's see if I can get that oriented the way I want it. All right, so we can use this idea of, you know, well, so we've established the idea that the distance is the area under the velocity curve. But sometimes we're not, you know, it's not just a nice stepwise velocity curve that we can just calculate easily. Sometimes we have, and sometimes we're not even given a function, we're just given data. So this is a really practical technique for analyzing data. In fact, I use this a lot when I was working as an engineer. Sometimes it's just easier to estimate the area under the curve instead of because I don't have a function. You know, it's not data that follows a nice function. So well, let's take a look at this example. All right. Anyway, suppose a car is moving with increasing velocity, and that we measure the car's velocity every 2 seconds. And here's the data. It's in this table, and we're asked to estimate how far the car traveled. All right. So let's plot this data here. So 20, and then 30, and then at 4 we're at 38. So we're just below 40. So something about there. At 6 we're at 44. So about there. 8 we're at 48, so about there, and then finally we're at 50. Okay, so we have some data. So it looks like, you know, I could estimate this. I could kind of draw a curve. Let me see if I can draw this decently. Okay, there we go. There's my curve for that data, and I want to estimate the area, right? Because I'm being asked to estimate how far the car traveled. So I want to introduce the concept of a right-hand sum and a left-hand sum. So we've essentially broken this. We can break this time. You know, we've got data every 2 seconds. So I'm actually, you know, we're going to break this time scale into 5 intervals, right? Every 2 seconds, because that's what we're given data. So, our change in time for each interval is 2, and we have a total of 5 intervals. So we say n equals 5. N is the number of intervals. Okay, notice we have 6 data points, but we have 5 intervals, so be careful about that. And one thing that we could do to estimate the area under this curve is just assume that this left-hand point continues until we get the next data point, and we just treat it as if it's a kind of a stepwise function here. Okay, so I'm going to estimate, I'm going to find my left-hand sum. Okay, so my left-hand sum, I'm using the left-hand data point, right? So for each interval. And so my left-hand sum will be the areas of, the sum of the areas of each one of these slices here. Okay, so I'm drawing, whoops, I'm drawing the left-hand sum here. All right, so you get the idea. What we have is a bunch of rectangles, and we can find the area of those rectangles just by taking the width. The width is the time interval, it's the delta t, right? And times the height, and the height is given by the left-hand data point. Okay, so the left-hand sum, I'm going to write it, I'll write it out for you here. I'm going to try and scroll this thing up without, yeah, well, I might lose it. It seems to scroll in jumps, but, okay, so I'm going to compute the left-hand, something what I'm going to call the left-hand sum. Left-hand sum. Okay, so we're just going to add up all of these rectangles. So the first rectangle is 20 units high by 2 units wide, right? And then the next rectangle is 30 units high by 2 units wide. And then we have a 38 by 2 rectangle. And then we have a 44 by 2 rectangle. And then we have a 48 by 2 rectangle. Okay, so we're just taking the left-hand data point as the constant velocity for that time period, just as an estimate. Okay, now obviously this is going to be an underestimate. It's going to be a low estimate, right? It's going to be too low. But now notice we've got this common factor of 2. So sometimes it's easier just to think of these left-hand sums as you're just adding up all these data points. 38 plus 44 plus 48, right? We just also have 5 data points, and then we can factor out a 2. Okay, so we can just basically add up all these first 5 data points and then multiply by the time interval. And when we do that, we get 360 feet. Okay, and this is a lower estimate. So I'm going to call this the lower estimate. Okay, so in this case, because we have this increasing velocity, the left-hand sum is the lower estimate. Now, if you have a decreasing function, the left-hand sum is not going to be the lower estimate. It's going to be the higher estimate. But in this particular case, the left-hand sum is the lower estimate. Okay, so that's our low estimate. Let's find the right-hand sum. Now the right-hand, oops, maybe I should use a different, I'm going to use a different color for this one. Okay, I'm going to write, oops, right-hand sum. Okay, so the right-hand sum, as you might guess, is we're going to use the right-hand data point as the constant velocity during any particular interval. So our right-hand sum is going to look like this. Okay, we're going to use this. Okay, so you get the idea. Okay, and of course these go down, right? So we're using these rectangles. Right. Wait, can't draw a straight line, sorry. But you get the idea. These are rectangles. I don't know why Yeah. Anyway, so now to get the right-hand sum, we're going to add up all these red rectangles. So, and we're using the right-hand data point as the height of those rectangles. So we're going to get 30 times 2 plus, right, because that's the, we're just basically adding those up. All right, so we have 30 times 2, and the next rectangle is 38 times 2 plus 44 times 2 plus, was it 48 times 2 plus 50 times 2. Okay, and again, I'm writing this out the long way, but a lot of times all I do is I add up the data points. So it's going to be 30 plus 38 plus 44 plus 48 plus 50, and then times the width of the time interval. Okay, so that's probably the way you'll do it when you do the homework, is just add up all the data points and multiply by the time interval. But I just want you to see where that's coming from. Okay, so when we do that, I got 420 feet. And of course, this is the upper estimate, right? Because obviously it's too big, right? It's too high. Okay, so but we know that our actual distance is somewhere between 360 and 420 feet. Okay, so let's go down just a little bit here. All right, so so one thing we can do to get even, a little better estimate is just average these two. So if we just take the average of these two estimates, we get, 360 plus 420 over 2 gives us 390 feet. So we could estimate this as 390 feet. And you could see that there's also a 60-foot difference between the upper and lower. So if we split that in half, we could say that this is plus or minus 30 feet. Okay, so, we have a lot of error in this particular estimate, right? We're plus or minus 30 feet, so a total of 60 feet on either, from the lower to the higher estimate. So one way that we could get a better estimate is to just have more time intervals. Okay, so here, this is the same problem, only now we've broken the time up into 10 intervals instead of 5. Okay, so we're going to get a better estimate, but it's the same process, right? If I graph this, let me just I'm going to actually pause the video. I'm going to do some work, because it's the same idea. It's just more time intervals, so it's a little more work. So I'm going to pause it and do some work and come back and then talk about it. All right, so I have drawn in my left-hand sum, and I've calculated both the left and right-hand sums. So in this case, the time interval is 1, and there are 10 intervals, so n is 10. And so I can just add up all of the left-hand data points, right? The ones that are in this, I've drawn a green curly bracket here. So I'm not going to include the last one, okay, because it's the left-hand sum. And again, the time interval is just 1. Okay, so when I do that, I get 371 feet. I'm going to scroll up a little bit. And then the right-hand sum, I'm just taking the data points from 25 to 50, adding them up and multiplying by the time interval, which is 1, and I get 401 feet. Okay, so those are now my upper and lower bounds for the estimate of my distance, how far the car traveled. Okay, and again, we could just take the average of these two, average, and so we're just going to take 371 plus 401 divided by 2, and we get 386 feet. Okay, so that's a little better estimate, obviously, because we're taking more, we're breaking our time interval into more slices. Okay, so we're, and in this case, there's what, what is that, a 30-foot difference between the upper and lower bounds. So this is, plus or minus 15 feet, okay, rather than what we had before, plus or minus 30 feet. Okay, so this is a much more accurate estimate. And you can see as we increase the number of intervals, we're going to get a better and better estimate. And these sums that we just talked about, these are called Riemann sums. So I'm going to write that out. These are called Riemann sums. Okay, and they are the basis for the integral. Okay, these Riemann sums are the basis for the integral, which is what we're going to talk about in this chapter and in the next chapter. So they are I can't write. I'm going to lose my train of thought. Okay, so let me go back here. All right, let me just write this out. Okay, and they are the basis for the integral. Okay, Riemann sums. Basis for the integral, which we're going to talk about in the next section. Okay, so just to give you a little preview, you can see as we increase n, number of intervals, we're going to increase the accuracy of our estimates, right? So here's an illustration of what it would look like for n equals 20, right? N equals 20 here. You can see we're going to get a better estimate than when n was equal to 10 or 5, right? Here's n equals 40. And as n approaches infinity, you approach the actual area of the curve, okay? So now in this case, again, this is just from your book. They assume velocity is positive, so they're not really considering displacement. But if velocity is positive, the total distance traveled is the area under the curve. Okay. So, all right, now one last thing here before we go. I want to look at some examples of linear motion with constant acceleration, okay? Because with constant acceleration, we don't have to deal with the Riemann sums and do estimates. We can actually figure out the area under the velocity curve with geometry. So let's take a look at this example here. We have a race car. It accelerates from rest at a constant rate of 5 meters per second squared. So that's 5 meters per second per second. Okay, so the velocity is increasing by 5 meters per second every second. And it's doing this for 5 seconds. So how far does the car travel? How far does the car travel at the end of these 5 seconds? All right, so here's the secret here of figuring this out. Okay, if you take physics, you'll learn some formulas, but this is the secret behind these formulas. This is the math behind it. So now we have constant acceleration and we're accelerating from rest. So we're starting here at 0 and we are accelerating at a constant rate. So our velocity is increasing at a constant rate. Okay, and that rate is 5 meters per second. So essentially the slope of the velocity curve is constant, right? And we could represent the velocity as a straight line where v is equal to 5t, right? Because 5 is the acceleration, right? And we can figure out the velocity at any given time just by taking the acceleration times that time. So now we know, let's see, what does it say? That we are going for 5 seconds. So if I drop a little perpendicular here, right? This is 5 seconds. So now you notice this triangle. Now this is this is 5 on the axis, but we could also consider the length of the side of this triangle to be 5, right? And we want to find out the distance just the area of the curve. So this is the distance that we're trying to find. So you see this triangle? We know the area of a triangle, right? We can find the area of a triangle, 1/2 base times height. Now, if we can find this height, then we can use the area of the triangle. And we know that V is equal to 5t, right? So when t is equal to 5, right, if we just let t equal 5, that means at the end of 5 seconds, we're going to be going 25 meters per second, right? Because we're accelerating at 5 meters per second. Okay, so this point up here, if I were to just draw this here, this would be 25, which means that this side length here is 25. Okay, so we have a nice little triangle here, and we know that the area of the triangle, so the area of a triangle is just 1/2 base times height, right? And the area of this triangle is also the distance, so, or the displacement, right? The displacement has to be equal to 1/2 5 times 25. So when we do that calculation, we get 62.5 meters. So this race car went 62.5 meters in 5 seconds at that acceleration. Okay, so the point here is that we can actually use geometry to find the areas under Sums curves, and in this case we have constant acceleration, right? So we're just dealing with a velocity that's just a straight line, and in this case it's just a triangle. All right, so let's take a little closer look at this one, just because this is where I start getting carried away. Let's do a little deeper dive here into this one. All right, let's create a little table here. Our acceleration is a constant 5, right? So the acceleration, if I were to graph that acceleration, it looks pretty boring, right? Just a straight line. And we already graphed the velocity, but so we're going to start out at rest. Our car starts out at rest, and then the speed increases by 5 meters per second every second. That's what acceleration means. All right, so there we are. We're at 25 meters per second at the end of 5 seconds. Okay, and this is what our velocity graph looks like, right? It's going to go straight up there. Okay. Now, we can actually find the accumulated change over time. So what if we want to know, how does the distance change over time? We want to find the accumulated change at various time points, right? Accumulated change. Okay, so obviously at time t equals 0, we haven't gone anywhere. We're at rest. So we're going to say that we're measuring everything from our starting point. So so we've got 0 displacement at that point. All right, so how far have we gone over the first second? So if we look at our little triangle here, right, there's our first second. So over our first second, our distance is going to be 1/2 times 1 second is the base of the triangle, and the height is the velocity, which is 5. So in that first second, we traveled 2.5 meters. All right, let's keep doing that. Now, if we want to look at the second, now we have a little bigger triangle, right? We've got so in this case, our base is 2 seconds, and now we're at 10 meters per second. Okay, so we're estimating the distance as the area under the velocity curve, which we can find exactly because it's a nice triangle. So if we do that calculation, we get 10. So we're at 10 meters in the second at second 2. All right, and then we just keep increasing our triangle here. So 1/2 times, now we have a base of 3 and a height of 15. So we get 22.5. Okay. If we go on to the fourth second, we have a base of 4 seconds and a height of 20, which gives us a total distance of 40. and, whoops, I wrote 1/4. I meant 1/2. Okay, and then 1/2 base times height, right? So in this final, at this 5th second, our distance is at what we calculated before, which is 62.5. Okay, so if we graph that, we get something very beautiful. All right, so you can see, just plotting these points here. Here we're at 40, and here we're at 62.5. Notice this beautiful parabolic shape that we get. I can't draw a nice parabolic shape. You get the idea. So notice a nice parabolic shape that we get. So parabolas are, they're quadratics, right? They have there's something squared going on here. So if the velocity is equal to acceleration times time, and the distance is equal to 1/2 base times height, right? So t times v, or v times t, right? That's what we get from the triangle. If we put those together, we get that the distance is equal to, I'm just going to substitute at for v. So I'm going to get 1/2 at squared. Now you might recognize that from physics, if you've taken physics at all. Distance equals 1/2 at squared might be familiar to you. Now this, of course, is assuming that your initial velocity is 0 and that your initial displacement is also 0. So anyway, I just think that's kind of an aside, but it's interesting that we can derive those physics formulas from this process. All right, I have a few more examples that will help you with the exit ticket. I don't have any practice problems in this set because I've got 2 problems in the exit ticket. I figure you got the Wiley homework, you got plenty of homework. So I'm starting to get up there in time, so let's go through these last examples here. Now in all of these cases, I am going to try to draw the velocity versus time graph. It's going to help me because the distance is the area under the velocity graph. So here we have a dragster stripped down, so there's no speedometer. And at maximum acceleration from rest, it travels 150 meters per second in 10 seconds. Okay, so again, we've got constant acceleration. So our graph is going to be a straight line. We're going for 10 seconds. And in this case, though, we're given the distance. Okay, and the distance is the area. So I'm just going to write it inside the area of this triangle. Okay. So, so our 10 seconds is the base of this triangle, and then our final velocity is the height of that triangle. Okay, so I want to know what speed it got up to in those 10 seconds, right? So I'm trying to find this final velocity. So, again, the area of this triangle, now it's going to be the distance, so the area is 150, right? And the area is equal to 1/2 base times the height. Now in this case, it's the height that's unknown. It's our v final, and that's what we want to find. So we can just rearrange this equation, and we find that the final velocity is 30 meters per second. Ta-da! Right? All right, so much easier than physics. All right, here's another interesting example. Whoops, what happened there? All right, again. Okay, so now here we've got a jet airplane speeding down the runway, and it needs to get up to 90 meters per second in order to take off. And if it accelerates at a constant rate of 2 meters per second, what's the minimum length of the runway? Okay, so again, we're going to assume constant velocity. It's accelerating from rest, so the y-intercept here is 0. And we need to get up to 90 meters per second. So 90 meters per second. This is velocity versus time. Okay. So again, I'm going to draw my little triangle here. So the time it takes is the base, and the height of this is 90 meters. Right? And here's the distance. This is the distance it's going to travel. And we also know the acceleration here. So again, velocity equals a times t, right? So, oops, yeah, right. So velocity is equal to 2t. Okay, that's the equation for that line. All right, so we have okay, so we've got to figure out in this case we're trying to find the distance, right? We don't know this final velocity, but we do know we know the final velocity, but we don't know how long it takes. But we could easily figure that out because we know that the final velocity is 90. So if we just plug in the final velocity into the equation for the line, we can solve for the time it takes. So that tells us that the time it takes to get up to 90 meters per second has to be 45 seconds. Okay. All right, so now we know this is 45 seconds. And now we can find the area under the curve, under this velocity graph, okay? Which is the distance. So the distance is equal to 1/2 times 45 times 90, which turns out to be 2,025 meters, okay? So we have to have a runway at least that long. That's the minimum length of the runway. We probably would like to have a little bit longer, just to just in case. But that would be the minimum length of the runway, because that's how far this plane is going to travel before it takes off, is 2,025 meters. All right, now this next one's an interesting one, because now we have we're dealing with a falling body under the influence of gravity. And gravity always pulls things down toward the Earth, all right? And the acceleration of gravity is 9.8 meters per second squared. But remember, it's pulling it down. And normally we think of down as being negative. Up is positive, down is negative. So effectively, our acceleration is equal to a negative 9.8 meters per second squared if we express it as a vector, right? Because now it has direction, it's pulling it down. So in this case, if we graph velocity versus time, okay, I'm going to put my time axis up here because I'm starting at rest, but it's being pulled downward. The velocity is negative, right? So the slope of my velocity graph is negative, right? This the equation for this line is going to be the velocity is equal to a negative 9.8 times the time. Okay, so this is velocity versus time. Okay, but we're dealing now with a negative acceleration because it's pulling down. Okay, but again, I can figure out my triangle here. All right, so I guess I didn't read the whole question here. We're dropping a ball from the top of a 45-meter tall building. Okay, so we're 45 meters high, and we're asked how long will it take the ball to hit the ground. Okay, so we know that it's going to fall in the downward direction by 45 meters. So our distance is a negative 45 meters, right? Because it's falling down from its starting point. Okay. And I'm just going to call this T final, right? This is how long it's going to take to fall that 45 meters. And this is its final velocity, okay? Okay, well, all right. We have the area, but we want to find how long it will take and how fast it will be going. So we have two unknowns here. But we also know the acceleration of gravity, so we know the equation of this line. So V is equal to negative 9.8 t, so our V final, right, is if we plug in T final, we get V final. So our final velocity will be negative 9.8 T final. Okay, I can write it that way. And then I know that this distance is equal to 1/2, right? I'm writing the area here of this triangle, 1/2 v final, t final. All right. All right, so now I'm going to plug in some of these numbers. I have v final. I can plug that in, right, in here, and t final. So I can eliminate a variable, right, just by plugging in this expression right here for our final velocity. So I get 1/2 v final times t final, which is t final squared, right? So I will get 1/2 times negative 9.8, right? That's times t final, but then I'm going to have t final times t final, right? So t final squared. I can write it that way. And I know that that distance, we're told that we're dropping it from a 45-meter tall building, so I know that it's going to travel. When it hits the ground, it has traveled 45 meters in the downward direction. So that has to be equal to negative 45 meters. All right, so now I can solve for t final. So t final is just equal to the square root of negative 45 over 1/2 of 9.8 is going to be negative 4.9. Okay, if I take the square root of that now, negative divided by negative is positive. Take the square root, I get 3.03 seconds. Right? All right, so that answers one part of the question. How long will it take to hit the ground? Now I want to figure out what the final velocity is. And all I have to do is go back up to this equation here. And so v final is equal to negative 9.8 times the time it took. Okay, and that's equal to negative 29.7 meters per second. Meters per second. Now notice it's negative because obviously it's traveling in the negative direction because that's the way we set our frame of reference, that up is positive and down is negative. So it's a negative velocity because it's traveling in the downward direction. All right, bear with me. We've got one more example. He's driving his car. He's going to get on the freeway. So he has to accelerate down this on-ramp. And we're told that his initial velocity is 13 meters per second at the beginning of the ramp, and he gets up to a speed of 27 meters per second at the end of the ramp. And it takes a total of 15 seconds to complete that process. And we want to know how long is the on-ramp. So again, I'm going to graph velocity versus time. Velocity, time. Now what does this look like? You're starting out at 13. Let's say this is 13. And you're increasing your speed up to 27. Right, so here's 27. All right. Now we want to find the area of that curve, right? Because the area under the velocity graph is the displacement. We're also told that it takes 15 seconds. So we know that this distance here on this shape is 15 seconds. And so this over here is 13. This distance here is 13. And this distance here is 27. Okay. Now what shape is this? This is not a triangle, right? We've been doing triangles. But notice that this is a trapezoid. Okay, so for a trapezoid, the area of a trapezoid now normally we see trapezoids are kind of like this. They have two parallel sides and two non-parallel sides. Now here the parallel sides are going up and down, right? They're going in the vertical direction instead of being horizontal. So this is sort of like a trapezoid oriented vertically instead of horizontally. But if we have a trapezoid, just a general trapezoid where this is the height h, and we have two what they call bases, b1 and b2. Okay, and the formula for the area of a trapezoid is 1/2 b1 plus b2 times h. Okay, so in this case, we're going to use the area of a trapezoid to get the area under the velocity curve and compute the distance. So in this case, our bases are 13 and 27, right? Because we've got it. It's turned 90 degrees. So the distance is equal to 1/2 times the sum of the two bases, which is 13 plus 27. So basically the average, right? And times the height. Now in this case, the height, because we've turned our trapezoid on its end, our height is 15 seconds, right? So if I calculate that out, I get 300 meters. Alrighty, well that ought to be enough examples for you. You'll be glad that I cut a whole bunch out of this lecture. I decided not to. There's so much more I can tell you, but oh well. This is not a physics class, so I wanted to limit it to just the things that you needed to know for the homework, and then some, but you know. All right, so I will talk to you guys later. Bye.